Hi, my name is Stuart Ozer, and this is Lab 5. So the purpose of this lab is to analyze the difference in simply dropping a ball and throwing a ball down, like this versus this. And we want to compare the bounce heights of both balls and the bounce times of both balls. So these are balls that are going to bounce back up, and we'll talk about how. So this lab uses only 3 fundamental physics principles. The force of gravity is negative mg when near the surface of the Earth. The position update formula, where the final position equals the initial position plus the derivative position velocity times delta t. And then the velocity update formula, where final velocity equals initial velocity plus the derivative of velocity acceleration times delta t. Acceleration here is F net over m, because F net equals ma, so Newton's second law. So if we look at the main results here, you can actually see that the initial push one, that's the second example I did, it hit the ground sooner, which is to be expected, and it actually bounced a bit higher. We'll talk about why. So first of all, though, the systems and surroundings. The system was ball 1, ball 2, the plate, and the Earth. That's everything. The plate's the thing it's bouncing on. And then the surroundings is nothing, because everything's in the system. And then the initial conditions, the ball mass is 0.624 kilograms. That's the mass of a basketball. And then the ball height is 0.5 meters. And then we'll talk about one other thing that's not necessarily an initial condition, but it's something that matters. So here's the code. So after we set up what the ball is and stuff, we then take the ball and we establish its mass to be 0.624, and we give it a position of 0.5 meters above the plate. And then we set g to be 9.8 meters per second squared. And then restitution is 0.8. That's the amount of energy the ball retains every bounce, and it's going to maintain with a COR, coefficient of restitution, of 0.8. So then we calculate if the ball has bounced, if it's collided with the plate, and then we flip the velocity, and then we multiply it by the restitution. So we don't want to get the same amount of velocity. We want to lose some. And we'll actually look at that in a little bit as well. But then we apply the velocity and position update formulas, and that's the code. So looking at the main results here, we have that the initial push hit the ground sooner, which is to be expected because 0.5 was after the vertex of the first drop. And then we have that it actually bounced back higher. And why is that? Well, it bounced back higher because it had a higher initial velocity when it hit the ground, because it started with an initial velocity, then it was moving faster when it hit the ground, and thus it bounced right back up, farther than the other ball bounced up, the rest ball. Now, there are possible sources of error here. That would be that mainly human error, because this is all coding, and so the code's not perfect. In some cases, if the ball was dropped from too high or too low, or the reciprocity was just not enough, then the ball would bounce once and then flatline, and that may just be a problem with like my delta t, or another problem that needs to be analyzed. But that's why I use these actual values, because that's what made them work, and that's something that needs to fix it, and that's because of human error. Now for the what if questions. What if the ball was launched upward? If the ball was launched upwards, the height of the bounce would increase still, as the height of the drop is higher, and the period of each time interval will remain the same as it was before. And then what if the ball gained energy when it bounced? Well, if the ball gained energy when it bounced, meaning the reciprocity is actually greater than 1, then the ball would bounce higher each time, and the period would increase every time interval. And so what does that look like? Well, that looks like this. So the first what if question on the left, you can actually see that the red graph kind of shifted over to the right because it's like we're throwing the ball. Because we're throwing the ball up, it's like we're dropping the ball from the same height as before, but now it's after we've dropped the other ball. And then for the second what if question on the right, you can see that the bounces actually get higher each time. Um, and then the otherwise everything looks the same except that your period is increasing instead of decreasing. And that's it. Thank you.